So hello everyone, this is lecture 35 for the solid state physics, in which we were studying about the crystals, and in the last lecture we discussed about the interplanar spacing and Miller indices, and I have given you this question to you. It is just same as this question, so you can solve this. In today's lecture we will start with packing fraction. So let's see what are packing fractions. So a normal formula we can see for the packing fraction is in 3D. It is effective volume of the atoms in a unit cell and the total volume of the unit cell. Okay, so effective volume of atoms, how can you find? So you just need to find the number of atoms inside a unit cell and multiply each atom with its volume, that is 4/3 pi r cube. We assume that atom is a sphere, that's why we take the volume of a sphere, and r is the radius of that sphere or atom, and n effective is the total number of effective atoms inside a unit cell. So this will give us the total number of, means the total volume of atom inside a unit cell, and this is total volume. So this fraction is called the packing fraction. Packing fraction. Now in 2D, how you can find? In 2D it is of area, means effective area covered by the atoms in a unit cell and divided by the area of the unit cell. So how you can find? So n effective, total number of effective atoms in a 2D space, multiply the area of each atom, that will be circular, pi r square, divided by total area of that surface. That's how you can find the packing fraction for the 2D. So let me give you an example. Like you have this kind of square lattice or rectangular lattice. So how you can find the surface packing fraction? So for this, how you can find the effective number of atoms? You have the formula, that is for four corners. You know the formula is, we can see it here. If you don't remember this, it will be a really big problem for you. So here is the formulas. So for four corners in 2D, you have n effective equal to 1/4 nc, that is number of atoms in corner, plus 1/2 nf, that is at faces, and 1 into n inside, number of atoms inside. So in 2D plane. Okay, so for four corners, let's see. It will be 1/4 into 4, it will be 1, and no atom at faces, 0, and no atom at inside, so 0. So for this we have 1 as the effective number of atom. Okay, so if it is 1, then area will be pi r square divided by the area of this whole lattice, that will be, if it is a, then side square will give you area, and a equal to 2r, r plus r 2r. So this will be your packing fraction for 2D and for a simple cubic, sorry, simple square. Now it can be of this rectangular also. So if lattice is this type, then how you can find the effective number of atoms? 1/4 into 4, that is of corner, that will give you 1, plus 1/2 multiply number of atoms at faces, you have 2 at the faces, so it will also give you 1, and there is nothing inside, so it will be 0. So total effective atom will be 2. Use the same formulas I just shown you. Okay, so remember those formulas. So it will be 2 into pi r square divided by, now area of this rectangle is this distance multiplied this distance, so this distance is 2r plus r plus r, it will be 4r and 2r, so 4 to the 8r square, so l into b. So that's how you can get the packing fraction for 2D. Okay, so in 2D you can have this kind of lattice also, hexagonal lattice. So how you can find the effective number of atoms? Now you have 6 corners, so you will use this formula, 1/3, and at corners that will be 6, plus 1/2, and at faces, so at faces it is 0, and inside you have 1. So at corners it is 6, so you will get 3 to the 6, 2 here and 1 from here, so you will get 3. So it will be 3 total number of atoms. Now how you can find the area? So there is equilateral triangle and it is 6 equilateral triangle. So root 3/4 side square, this is the area of one triangle. So there is 6 triangles, so 6 into this, you will get the complete area. And area of atom will be 3 into pi r square. So here you can see this side a equal to 2r. So that's how you can put here a equal to 2r, it will give you 4r square. And just packing fraction will be 3 into pi r square divided by this. So you will get packing fraction as pi by 2 root 3. Okay, so that's how you can find. Just remember these formulas, they will be very helpful, and these formulas all you need. So now let's see for the 3D cases. You already proved this in your elementary classes, but you can try. Prove that packing fraction for simple cubic now we have in 3D. So in 3D you know how to find it. A equal to 2r, and effective atom is 1 because of 8 corners, and you will get packing fraction is pi by 6. So it will be volume divided by total volume of this unit cell. So 1 into 4 upon 3 pi r cube divided by side cube. So it will be 2r cube. It will give you pi by 6. Same you can use the formula for BCC. Total effective atom will be 2, 1 at center, 1 at total of 1 all corners. So it will be 2 and effective, and here this diagonal side will give you this root 3a will be equal to 4r. Okay, so that's how you can find the relation between a and r, and you can solve, just use this simple formula and you will get the answer as this root 3 by 8 pi. You try to solve it by yourself, it's not that hard. So for FCC, you know, it will be at the face, and from there you can find root 2a will be equal to 4r, and effective atoms will be 4 because of 6 faces and 8 corners. You will get 4 effective atoms. So these, try to solve these questions, okay, and try to prove this, and remember these packing fraction, okay, for these structures. Now let's see some important thing, that is hexagonal close packed SCP structure. So now pay attention. Pay attention. Let's say we have a hexagonal lattice. So what kind of hexagonal lattice we have is, you already see this kind of lattice here when we start discussing this. Then when we were talking about the lattice, there I told you you can have different kind of lattice. So here it can be of a square, it can be of rectangle, or it can be of this kind. This is hexagonal lattice. Just take it in the 2D case, and then we can just continue this form to the 3D, and you will get the whole lattice. So remember this is the lattice. So for all cases, 2D, 3D and 4D, not 4D, okay. So this kind of lattice is called the hexagonal lattice, and we will use this. So here we were. Now we put a atom at every lattice, so we will have this kind of a structure. Let's say, just see this first layer, A layer, okay, we have put it like this. So this is hexagonal lattice. Now we will put atoms on the voids of the first lattice, means these voids, these are framed in the first layer. Then put the second layer on the voids, then you will get something like this, okay. Now there is 2 ways to put the third layer over it. So how you can do that? If you put third layer on this point, so if you try to put the third layer over it, so you can put it over here, then you will again get this first layer. So first process is this, means you will put the third layer over here, over here, over here, then you will get the A layer again. So that's lattice we call as AB type, and it is hexagonal close packed. You will get this type of structure, AB, then AB again, okay. So if we try to visualize this, then you see this is our hexagonal lattice, as I already showed you in the previous pages. So this is our hexagonal lattice. Now this is A layer, and if we call these, means see this A layer only, 1 2 3 4 5 6 and the center one. So these are like 1 2 3 4 5 6 and center one. Now on the second layer, it is put it on the voids. So we can see voids are here, here, here and here. So it is like here. So we put it these atoms. So this will be our B layer. Now what will be our third layer? There is nothing, it is just a line. Don't see that there is anything, okay. So when we put this third one, so it will be again on over the A. So that's how you will get A again, and these forms. So you will get AB type structure. Now if you try to find the packing fraction for this kind of structure, so how you can find? For that you need to find the effective atoms first of all. So for 3D structures we remember the formula. How you can find? It is 1 upon 6 for the 12 corners. There was this formula, 1 upon 6 into number of atoms at the corners plus 1 upon 2 number of atoms at the, okay, so it was 1 upon 6 into n into c. So at corners we have 12 atoms, but we will put 12 here. Then 1 upon 2 multiply number of atoms at the faces. So we have 2 atoms at the faces, plus now the total number of atoms inside this unit cell, so that will be 3. So we'll put 1 into 3. The total will be 6 here, 12, 2 here, 1 here, and 3 here. So we'll get 3, 4, 5, and 1 is 6. So to find the packing fraction, we need the volume of this whole unit cell. So how you can find? First find this area of this hemisphere. Okay, not a hemisphere, it's hexagon. Okay, so first find the area of this hexagon, then multiply with this side. Okay, total height, then you will get the volume of this whole type of structure. So we already find the area of this hexagonal, so it will be root 3 upon 4 side square multiply 6 because of 6 equilateral triangles. So this will be our area multiply c. So this is area and c is this side, this whole length is c. So this will be your total volume, and it will be 3 root 3 divided by 2 a square c. And here we can see that a is 2r because there is one atom and one atom, so a will be r and r, 2r. So there is this relation between c and a here. So c upon a ratio for this type of structures hexagon, it is root 8 by 3. Okay, so we'll use this relation here. Try to prove this. This is HW, that is homework. So substitute the value of c from here to here, and we will get volume as 3 root 2 a cube. And from here a will be 2r. We will substitute here, and we will get total volume this, and volume of atoms will be 6 because of total 6 atoms. Multiply 4 upon 3 pi r cube. So this will be our packing fraction, and this is equal to pi by 3 root 2. Now see, this packing fraction is equal to this FCC structure. So now we proved that for this HCP structure, packing fraction is equal to for the packing fraction of FCC. Okay, and that is equal to pi by 3 root 2. So remember this relation. Okay, so these are equal. So it will be very helpful for you. Now let's find the what kind of crystal it is. Okay, means let's find the basis of this structure. So what is basis? Basis means total structure is nothing but sum of these lattice points and plus bases will give you the whole crystal. Okay, so lattice of SCP, we know lattice, I showed you that it is hexagon 3 4 5 6 and there was one center. So there is how much lattice points you have, effective number of lattice points. How you can find? So you will find the using the formula of 2D. So that will give you this 3. We already find this, it was 3. So n effective, capital N effective is lattice points, so it was 3. And total number of effective atoms inside this unit cell is 6. So see, there are 6 atoms and only 3 points, so we will put 2 points at each lattice point, then we will get the whole structure. So how we find this? This is small n effective divided by capital N effective, it will give you basis. So 6 by 3 will be equal to 2. So there will be 2 atoms at each space lattice, okay, and lattice point. So basis will be 2. So that's how you get the basis, n effective divided by capital N effective. So this will be 6 by 3, 2. So these 2 atoms means because of this 2 we can see this is diatomic crystal. At each lattice point you will get 2 atoms. It can be of same kind or different kind. So these 2 atoms are at these positions, means I circled this. So this will be one atom and this will be your second atom will be here, and they form the system wall. Okay, so these are the basis points. So their coordinates will be, if you put 0 0 here, then it will be 1 by 3, 2 by 3 and 1 by 2 for this. Okay, so remember this. And this SCP is nothing but diatomic crystal. It will give us diatomic crystal. So this is all you need to remember from this hexagonal close pack structure. Very important. Now we will see some structures which are important from the exam point of view. So first it is NaCl structure. We know we call it rock salt structure. So let's see what kind of structure NaCl has actually. So it is assumed that it is to be made of two interpenetrating FCC lattice, one displaced along edge axis by 1 by 2 of the edge length. So what is the meaning of this statement? First of all, forget these dark and the hollow circle. Okay, let's say we have only FCC. You know how it look like when we have FCC structure. It will be 1 2 3 4 5 6, means on the faces and on the corners only. You don't see this yet. Okay, these are not here. See this FCC structure only. Now what is it saying? That two FCC structures are interpenetrating, and means we will just stretch this whole crystal out parallelly. Stretch this crystal out, then we will see that there is two atoms at each point, Na and Cl. Now when we stretch it out, then sodium atoms will came out and Cl will remain there. So from there it was 2 there, now Na will came out half length, Na will came out half length, and then it was here, from here also Na will came out half length, and in the middle also, means just see this FCC structure first, then stretch out one atom from every atom, okay, to this parallelly. Then the structure you get will be of NaCl structure. And okay, so NaCl structure you will get. Same here also, it will be somewhere here sodium atom, and Cl will remain here. So this dark spot represents the Cl and the hollow spot represents the sodium atom. Okay, so that's how you will get the structure. So now let's see the packing fraction for this crystal. First of all, we need to find the effective number of atoms inside this unit cell. So how you can find? We'll use the formula for the 8 corner. So for 8 corners it will be 1/8 NC plus 1/2 NF, that is faces, plus 1/4 edges NE, because here we have on the edges also, plus 1 into N inside. So we have 8 at the corners and 6 at the faces, all 6 faces, and on the edges we have on all the edges, so it will be 12 edges, so total will be 12 plus 1 inside. So this will give us 1, and this will give us 3, this will give us 3, this will 1. So this inside one is of sodium, and these 3 we get it at the edges, this will be also for sodium, and these 6 on the faces it will be of chlorine, and on the corners also you will have of chlorine. So total number of effective atoms will be 8. Now packing fraction is nothing but volume of the atoms divided by total volume. So there will be different radius for different atoms, Na and the Cl. So we'll see that there are 4 Cl and 4 Na atoms. So 4 into 4/3 pi r of Cl cube plus 4 into 4/3 pi r Na of cube. Okay, so we have taken the different volumes. So this will be total volume divided by. Now we will see this length A. This is of R plus 2R plus R. So this 4R will be equal to this radius is of chlorine, this is of chlorine, and this is of, so 2 radius of sodium, 2 radius of chlorine. So A equal to 2 radius of chlorine plus 2 radius of Na. So take the 2 common and RCl plus Na, so it will be this, means A cube will be the volume of whole this lattice. So 8 RCl plus Rna cube, this will give us total volume. So this will be your packing fraction, and if we solve this further we will get this equation. Now there is a very interesting relation. When we say that radius of chlorine and sodium are nearly equalize them, then we will get the packing fraction as pi by 6. Okay, and this is the packing fraction of simple cubic. So that's why we call the structure of NaCl as simple cubic, and also we call it rock salt structure. Okay, so let's see the basis of this structure, how we can find the basis. So first we need to find this lattice point, effective number of lattice points. So take this one side. Okay, so there are we will use the formula, means for the simple cubic we know there are only 4 corners, so it will be, means see this, now 1/4 into total number of atoms at the corners, that will be 4. 4 at the edges, means at the faces, means see the 2D structure of this, so you will get something like this, and 1 inside. So 4 at the faces, 4 at the corners, and 1 inside, so that will give you 1, and 1/2 into 4, that will give you 2, and 1 inside, so total lattice point will be 4. Okay, and effective number of atoms inside this unit cell are 8. So how you can find the basis? Just divide the total number of effective number of atoms with the effective number of lattice points, so this will be 2. So at each lattice point there will be 2 atoms, only then the total atoms can be 8. See, 2 4 is 8, so this relation will always be valid, and these 2 basis atoms will be at the 0 0 0 and 1 1 2. These will be their locations, so this is 1 and this is the other one. Okay, means this and this. So if you find the coordinates, you will get these coordinates. These are the basis atoms. So this was NaCl. Now let's see one more structure, that is of cesium chloride. It is assumed to be made of 2 interpenetrating simple cubic lattices, one displaced along the diagonal axis by 1/2 of the diagonal length. Okay, so what is the meaning of this statement now? So it was 2 interpenetrating simple cubic lattices. So we have 2 simple cubic lattice, and it is stretched along the diagonal. Now it was stretched along the length edges. Okay, but here we will stretch it along the diagonal. So first forget this, this is simple cubic. Now there is 2 atoms at this point, cesium chloride. Now if you stretch it along the diagonal, so the 1 atom will came out. Okay, and 1 will be here. Now first one will be here. So now the resulting structure of cesium chloride will be BCC. This is body centered cubic. So from here it will go like this here, so this will be again a BCC structure you will get. So for cesium chloride you will have BCC structure, and you can easily find the packing fraction of this BCC structure. You already know it is √3/8 pi. Okay, because when you put the RCS equal to RCl, you will get this value. And how you can find this is just diagonal, you will see it will be 4r equal to √3a. Okay, and a will be equal to this, means this is not 4r, means this will be sum of the radius of this one and radius of this one, so they are 2 different radiuses. So if all are same, then it will be 4r equal to √3a. So if you take this value, then you will get packing fraction as √3/8 pi. Okay, it is just same as this. See, BCC structure √3/8 pi. So if we find the basis of this structure, then it's just, see, for the simple cubic, take this 2D structure, and it is just corners atoms we have. So 1/4 into 4, no edges and no center, so you will get 1 as the lattice point. And you know how much atoms, effective number of atoms are 2, so 2 divided by 1, you will get 2 as your basis. So if there are 2 atoms and only 1 lattice point, so all 2 atoms will be at 1 lattice point, so basis will be 2, and its position will be 0 0 0 and 1/2 1/2 1/2. Okay, so we take origin here, so it will be 1/2 1/2 here, and we call these as diatomic crystal. So this is also a diatomic crystal. So try to find this for the CSCl, put the radius equal, you will get this value. Now let's end today's lecture here. In the next lecture we will start with XRD, that is X-ray diffraction. Okay, so thank you everyone.